Good afternoon, and I'm so happy that Dr. Bonus is behind me. He gave a talk, and last year we met in Goa. And I'm so lucky that I meet many colleagues of coming from all over the world, and this is one of the I'm sharing my some of the academic. I can say some academic I've done in the Baba Research Center. Where Baba Research Center having around 4,000 scientists in that. Okay, so this is part of the this is our senior colleagues. They also part of the Department of Immunology. There will be huge plans for all science, all engineering is there. So this I working in chemistry division. So today talk is just sorry. There are top Phospors to quantum dot and Nobel Prize emerging methods. So that's sorry. I just my talk is actually something in the what is luminescence and how useful to the real art and how the quantum dots and how this I come to some of the emerging field of research. And this is luminescence, the process of emission in the ultraviolet light or infrared, or the suitable light or the mechanical force or energy is provided to this substance. Depending on the source of the light or source of the light or force, the bioluminescence, chemiluminescence, textureluminescence, and electroluminescence, photoluminescence in the picture. So two types of the photoluminescence, or you can say this luminescence, photoluminescence, you can say you have down conversion and up conversion. What is down conversion is energy absorbed from ground state excited state come back to track level, then emission occurs. We hear emitted energy is less than absorbed energy. And in case of opposite, of conversion cases, the electron goes from ground state excited state, and then before coming down, another electron hit. Okay, another electron hit again go to the higher excited state, E2. Okay, E1 to E2. Just from the E2 level, energy come back, the electron come back, electron falling in stack space, and this is like this up conversion. So here, the emitted energy is less than more than of the absorbed energy. So why need electron arrows in the phosphor semiconductor? This is why. This is one of the this one. You see, this is the periodic tables. I think I want to remember that about to 19 and the 150 years celebration of Mendeleev, and he was born in the Russia. I also giving talk in the time many places how the Mendeleev table has come up. So one of Mendeleev tables today we see modern periodic table is which goes to the many scientists, but particularly Mendeleev. So this is 17 elements. You can see scandium, yttrium, lanthanum, and cerium to lutetium. These 17 elements. We have to talk about it and our previous speakers talking because they are found in the many similar oxide or monazite are found similar, but extraction is tough, it's different. But otherwise, cerium is high abundance in our art. So the internal compounds you see uniform oxide as one compound. They have luminescence very soft, big because of wave transition, but they have poor luminescence. Okay? But if we drop in the internal compound of the list, the semiconductor have the valence band conduction band at the around transition, but for not around transition. But if we drop some small amount, the luminescence intensity can be increased by elation from semiconductor to the dendritic because the dendritic having the dendritic concentration is happens because of the interaction. But the advantage of the time is that there's a large number of photons can be absorbed through the bankable semiconductor, and in this many electrons from valence band conduction band can be brought, and then this electron holding takes the emission, but the rare earth is nearby, and the rare earth can absorb this light from the semiconductor. That is why we are dropping this in the semiconductor or insulator. So just brief on it because I will not explain too much about the Nobel Prize in 2014 in physics is coming from the Akashi and Amano and Nakamura. And they started, I think this Akashi and Amano, they started in 1990 and Nakamura has joined, and they've got the known flies and the blue light emitter. This is called gallium nitride base. But the question is related: what are all gallium nitride base? Because gallium is one of these rare metals. Is only this solve the problem like metal? No, we need rare ions. White light or any colors. These are rare very, very important. So in the progress of mechanisms, I published one in 2015, but before that, I showed gallium nitride important. This 726 announcement from Nobel Prize came in gallium nitride. I'm very lucky that this here you can find gallium nitride. But today, most of people talking borite, say nuclear borite, something people talking because the permanent magnet. But if we see this review article, you can see meaning nitride and graphite that have large coercivity. It is much better than neodymium base. You see some of you can see this paper of my progress material science. This you can see. This is the one of the infected around 48. So this is the real order of nanometer and just to give example. So this is the electron absorbed from very small conduction band in its transfer to the real order and real order produce better emissions. This is one of the source that. And this is one of the I want to tell you. I think real order very important. Today, many people has not think that water can be stable up to 100 degrees centigrade. We have published paper that if the Y24 system in that when the helium when the water is there in the the hexagonal structure and in a tube, water can be removed up to 500 or 600, up to iron they can only remove. What about the flow? Why did this compound degradation? Compound become tetrahedral phase. When you putting the helium or helium amount increases, this comes to the tetrahedral phase, and then heated 100 degrees Celsius, 900 degrees, they become tetrahedral phase. Again, no necessity here because water is a concept. This is the one we proved in this paper. Also, the same thing, Bismuth also we published the same thing last year. That's also just paper as it is without any review. And same thing with Bismuth will do. If Bismuth gets a more luminance enhancement, this we again publish that against consecutive years. This is super. I will explain today many that one. I expect others also. Here, another word I explain you. This is the one of the student etherial phosphate. Here, this compound you see here. RAREMET shows green and the red emission, but you don't find in green light and 500, and the red comes 650. This is first report that this compound 12.5% containing they remove the green emission because of red emission. This is the first report that we have published. This more than 60 citations this year. This paper. This can be used. I told you upcoming part can be used. Why upcoming part is used because we using the near infrared light and the nanometer or 980 laser because of the potential gap is 1 centimeter there. So this can use for the imaging. This is one of the imaging can be used. That's why the photo evidences one day can be substituted on this imaging purpose, photo evidences one day. This is I will bring in here. And after this, I want to bring in a quantum dot. The quantum dot is a superconducting matrix. Their particle size are in the narrow range, but which is less than excited voltages. Many people talk quantum dot depend on the narrow size, but not always. Their particle size should be less than excited voltages. When is sufficient? Sufficient photon light is absorbed by the quantum dot. It can generate a cycle, electron hole pair through the Coulomb interaction. Depending on the particle size, absorption peak varies. In general, absorption peak position shift to the shorter wavelength when the particle size decreases. The absorption population of quantum dot is very high, higher than bulk. This quantum dot compared to the bottom up, bottom down approach. Last 40 years, the potential has been realized in the various applications like sensor, dynamic catalysis, and bioimaging. This is the one to express the what is this function. This gallium arsenide and indium arsenide and gallium arsenide. This is the today's system. If you see in the band gap of the gallium arsenide is a 0.35 and gallium arsenide is a 1.42. The shadow is this. The electrons is excited by absorbing the frequency, suitable frequency, resonant frequency. The electron goes from the ground sector excited. You can electron hole pair formation, and they can produce the emission. But if you having their potential energy is they are having current energy maintained, they can stay as long as. So this is one of these quantum dots. So you have this user band gap and then have the valence band, condense band, and this continue. But when particle size decreasing, the continue to stop and the discrete energy level. This is the quantum dot important is the light emitting diode, photoconductor, and photodetector, and catalysis, and bimetric and photovoltaic. So this is I want to tell you in the world history. If you see how this coming in the picture. 1930s, if you see two film transmission microscopy SAM started. If you see transmission microscopy SAM started in Germany. They started. This one revolutionary. 1950, transistor and video pocket started this one. And the 1960, the molecular beam HPTC and 2D method. 2D method was graphene is one of the two Nobel laureate come from the Russia, but they are certain in UK, they got a Nobel Prize, but they are origin from the Russia. And the quantum dot, quantum confinement 1980, this also start from Russia. So this is want to tell you from Russia at that time they gone Soviet Union, so USSR 1990. See this Ekimov has people copper chloride, part in the glass system, and he published paper in the early Soviet Union. But many people did not recognize his work. This please identify it because the paper is citing only 150 citations because the paper writing in the Russian journal because of it was cited. And this you see this Ekimov and his PhD. I think hopefully his PhD guy published paper, and but they mention here quantum size effect in the three-dimensional microscopy. This is first report that quantum confinement started in the experimentally. You see here, this is here particle size. In the particle size, you see around 31 nanometer, and when it comes to 2.5, band shifted with the lower wavelength. This is first reported copper chloride question and put in glass system how the particle size change the optical. This is just paper come this Nobel Prize work already from this optical emission means it's a spectrum. And this is what I just in the same year, the Bruce and that laboratory United States was unaware of the Ekimov's work, observed the size dependent quantum effect in the dimension 5 floating fluid in the solution. His theory, but Kimmel Bruce theory model on quantum size effect. All the assumption was established and confirmed experimented many scientists. This is a Bruce. Bruce has his work in the UC here. He prepared Kimmel 5, and this quantum side effect is started. But this before him, this Ekimov from Russia has started. And he used to do a famous equation of the BC in the quantum side. He studied. You can see a Bruce equation. You can see here how the Hamilton equation of the the electron Hall kind energy and the potential energy. How come the energy? This gives rise to how the absorption peak shifted. Absorption this energy shifted. This you can explain this. This is one of the again. One interesting was that and this buoyancy and from this buoyancy also joined in the Bruce lab. I think buoyancy seems to be his France, but he's in United States. And the Ekimov also now settled in United States. This buoyancy also I think he started working the Bruce as he's a postdoc. And they also published some papers. I show you some papers published. And 1998, buoyancy started his postdoc training at the Lewis Laboratory, where he learned people should keep a quantum dot. There was a need to improve the method to prepare monocyclic particle because because otherwise the particle you're keeping long time because the edging effect, the changing peak position. But now you prepare monocyclic particle using hydrophobic the ligands like the oric acid. You can keep long time. This is he can control this. So he published with the paper the Murray and very famous this paper. But the Zach's paper, the American Chemistry Society the 16. This work and these three work has been given this. You see here, particle size from 1 to nanometer to coming to the when you can peak is shifting to longer. It was big. This is the one we did. So the significance contribution of the committee using the quantum dot was recognized by the Nobel Committee for Chemistry and by Buoyancy and Lewis and Ekimov. Hopefully Ekimov is a physicist. I hope that he's a physicist. But they got him, but he is settled in the United States. Yeah, so now quantum mechanics, in fact, we see, in the model, you can see quantum wand. In the time quantum wand, you see two-dimensional electrons can be around, and the quantum wires, one-dimensional electrons around, and then quantum dot, zero-dimensional electrons. This is one of the iron extreme tumors. And one of these I contributed in the, what contribution you may ask you, yes, we have prepared compounds. Suppose some of the compound doesn't shows because shows very small voltages like SNO2 European and GI2. They have a certain voltages around 3 nanometer. So the particle size more than 3 nanometer, you're going to produce a sort of voltages, or you're going to produce a quantum confinement. But we prepare the SNO2, but put in a GI2 matrix, you can produce the, you can produce this excited voltages or quantum confinement. This is I think we listed in here. So I illustrate this again. Xenon excited in the another was one SNO2 and Y2T. Y2 is a band gap around 6 electron volt. So tin oxide is around 3.6 electron volt. You put higher, you can get a generate excited. This is what we have initiated. I have explained to us. You see here. You see this excited generation by the two simulator interface. This was initiated in years. So this also another was actually how to prepare modular part in quantum dot. In the time you see RAREMET is a reducing agent, the series of magic size cluster, and the quantum dot. Why magic size cluster means magic size cluster is like before quantum dot, some few molecules like 40 molecules something. This 30 molecule gives you this magic size cluster. This we publish in this one. And you see here this PVC quantum dot bends around 500 nanometers because of this cluster, magic size cluster, and the EV particle size increases. You see that the band shifted to longer band. And this is light harvesting photovoltaic. We have done this one. We have done experiment here. By using this, we are using the tandem. The now photovoltaic is using different absorption peak. And then they can improve the photovoltaic activity. So here you see here, I use the PVC quantum dot to prepare large quantity because the PVC quantum dot having the certain bodies of 48 nanometers. Your particle size and the 48 nanometers is for quantum confinement effect. So I combine all particles and we do the studies of the photovoltaic studies. This is some of them we have published. They are not they can absorb left light. And this efficiency improves so much. This is the one. So this emerging methods, how we can say emerging method because many people sitting in different coming from a different area and this one. The argon dot fiber amplifier is one of the important methods. We should be considered this emerging field because this is the today digital communication. Because silicons was used from one of the I think we call it Nobel Prize. I think I forgot is from China, but certain US something. He was silicon fibers, but now hydrogen fibers, dot fibers will be emerging fields, we want to say. Now we are the emitter because I told you, like emitting diode, whenever the produce something, whenever you can see I sometimes problem comes because of the one white light or called hot light. So always some red emitter was missing. Okay, emission was this we need this was producing the apart from the green light blue emitter. Another layer of dot light emitter because this was important because okay, today our imaging is our body is full of the water, so they absorb they absorb light. Okay, so these are the two second photon, second photon, third photon, they absorb light, so they cannot be used. So you have to use in the near light emitter because around 1500, 1100 nanometer, they be better than they can have better resolution. So this near light emitter is important in the medical fields. The real top quantum cutting methods I told you to improve that I use silicon. Now people use YB doping again. They improve this quantum cutting effect because you can increase up to 200 the efficiency. There are top photo evidence. I told you that to the medical fields, one day photo evidence will change all detected because they have the huge emission intensity. This unbelievable. Quantum dot perovskite halide. I think perovskite halide is now just last 10 years emerging. This also one day I hope the quantum dot one of this emerging field media. And 2D matrix, actually, 2D matrix meaning modern disulfide is one of the emerging field junction sulfide, because when when modern sulfide is semiconductor, when it changes to 2 dimension, they become metallic, sometimes insulator, or means this band gap increase. So this is one of 2D matrix is one of the emerging field in the scientific community. And acknowledgement, thanks to this one, and the my director now is shifted to other places. My colleagues, distribution, Robindo, Ghost, Rowan, Frank Dragons, where most of the some of them I did with him, quantum dot from Victoria, and some of Texas you can see from the internet that for this project for this. And thank you for the listening.
It was really exciting talk.